Hi everyone. My name is Dheeraj Kumar Narang, and I'll be speaking on the topic of engineering framework to assess equipment reliability of airfin coolers in process plant industries. So I'll just briefly introduce myself, and we'll just get into the topic. And at that point, I'll turn off my video. Uh, so a little bit about me. Wait a second. Uh, I have around close to 13 years of experience in the energy industry. I worked in North America, Middle East, and India. I'm also doing my PhD on the side with Harrisburg University. My field of expertise is corrosion, mechanical integrity, digital product management, and technical PM in hydrocarbon and chemical processing plants. My interests are critical infrastructure, reliability, smart asset management, and so on. So that's just a brief about me. So we'll just get into the topic now, and I'm gonna stop the video. Hang on a second, just give me 1 second. Yeah. Okay. Good. So the purpose of the presentation, why are we here today? We will be describing the importance of FMCA method in reliability assessment of complex assets. Now, I know the title I had is airfin coolers, but I'll just, explain what I mean by a complex asset and how, we can apply this method, not just for airfin coolers, but also for the other complex assets in the industry. So let's get into it. Hang on a second. Yeah. So we'll cover highlighting the challenges with the remaining life assessment of uh, complex assets in process plant in industry, and uh, let's see. Oh, sorry, I thought I had a question. Sorry, never mind. Yeah, and I will unveil the FMCF framework. I call it a holistic method because I'll explain why and why we need a holistic method for complex assets. And then I will also demonstrate the application, the practical application with a case study for one airfin cooler and one well stimulation service units. So I know the title had airfin coolers, but we can also apply this method to other assets. So that's why I also included an example of well stimulation service unit. And I'll explain what a WSS unit means, how it looks and stuff. Structure of the presentation will describe the assets in available in the process plant industry with the context of mechanical integrity and reliability engineering. Then we'll go over the major challenges with the asset management for each type of asset, and then I'll explain the method, the FMCA method, the full form of which is failure mode effects and criticality assessment. We'll go through the steps, the criticality analysis, types, standards, and guidelines. Then I'll also demonstrate developing an FMCA worksheet for process plant assets, and we'll cover two examples. One is well stimulation service unit, and one is airfin cooler. There you go. And then we'll also cover the business benefits and importance of holistic method. Like, why are we adopting a holistic method? What is the use of it from a business standpoint as well? So let's dive into it. Process plant assets. This is a typical sample PFD of a poly isobutane unit in a refinery. So you can see we have fixed equipment. We have a vacuum flasher. We also have saws, piping, valves, pipe fittings, and there is also a pump. So let's see, fixed equipment. That's one type of asset: reactor, distillation tower, pressure vessel, heat exchanger. Second would be piping and fittings. It could be across hydrocarbon, chemicals, and utility systems. Sorry. Rotating equipment, pumps and compressors. And then we'll also have the auxiliary equipment such as silencer, agitators, and mixers. They may not be shown on a simplified PFD, but those are also present in a plant. And then the instrumentation fittings, digital controls, and to manage everything, we also have the digital assets, the information system. One example would be an inspection data management system, a PSV, pressure relief device, or a pressure safety valve, design and like your use cases and testing system. And it could also be a sophisticated condition monitoring system for a rotating equipment, vibration sensing and all those things. So these are the type of assets are present in a process plant that either directly touches the equipment or the containment or the process fluid, or indirectly, for example digital assets or instrument fittings. So how do you assess the remaining life, or do a condition assessment for all type of assets if they are combined into a package unit? And we'll go over it. So let's go over the asset management strategies. What are the typical ones? So we can bifurcate all types of assets into three: fixed equipment and piping. This type of asset deal with primarily the loss of containment scenarios, because the integrity is more important. If there is a leak, it's a failure. So those mechanical integrity and the failure would be defined as a process fluid leak. So there are industry best practices: API 571, 510, 570, ASME, National Boiler Inspection Code, and so forth. If you have a very specialized chemical plant, you can also use Materials Technology Institute, MTI's specialized damage mechanism libraries, and so forth. So the failure mode is different. It's mainly the process fluid leak. Now, uh, rotating equipment, the loss of functions is scenario is the main one for roto, because most of the time you will have a spare pump or a spare compressor to or a compressor train to be available in case the main one shuts down. So the failure is more like asset not being operational, or if you have a spare, or if you don't have a spare, then there is a change in your criticality as well. So one would use a reliability center method, because the functional failure is the main scenario here, and API 691, which is risk-based machinery management. This is a new standard, API 691, and it's slowly becoming popular. I think it came out in 2017, so it's very new. It's newer than the API 580 for fixed equipment, but it's I think it's going to be widely used in a few years. Then you have your package equipment, or as I call it, a complex asset. Now, you could also have a case where you will have both fixed equipment and rotating equipment as your sub assets. So, how do you assess? How do you build an asset management strategy for that? There is no singular mechanical integrity or a reliability strategy for that. So, how do you do it? So, let's take a look at a one packaged equipment, one complex asset example, and then we'll come to know what I'm highlighting here. So let's see reliability engineering challenges for complex assets. Like I said, it will have everything: fixed equipment, piping, rotating, dynamic equipment, and instrumentation. In some cases, hydraulics as well. Uh, and it's difficult because we don't have a single method. There is no single industry best practice, because the functional failure, the failure mode could be different, the way it fails. And there are different terms for failure modes as well. Some people use it failure mode, some people use it failure type. It's all depending on the context of the industry. You can apply that. Okay, how do you simultaneously assess the loss of containment and loss of functional failure modes? How so that's the main challenge. And then the example would be a feed filter package in a DSDT unit, air fin coolers, widely used, all types of process plants, and well stimulation service units as well. Okay, so this is an example of a complex asset, air fin cooler. So you can see we have the dynamic components, the drive assembly, pumps, and there could be a fan ring, fan, blades, and then you also have pressure containment like a header box and the tubes. So for the tubes in the header box, the failure would be loss of containment. But for the drive assembly and for the fan ring assembly, it could be airflow, lack of airflow, insufficient airflow, and so so forth. So it's different. Let's look at the another example. So let's look at well stimulation service unit. This is how it looks like. So WSS unit is used in hydrocarbon upstream industry, especially onshore, where you have oil wells already drilled. but you need to, service the oil wells to take more oil out of it. Or you could also do, drilling, fracturing, and all those things. So this is one type of the WSS units. In my career, I've also dealt with coil tubing units, blender units, and so forth. I think there are like 14 or 15 types of different well stimulation service units. So let's break down this unit as well. So we have the APO tank, the acid pumping unit tanks, and the piping. We have the triplex pump, which is going to pump the acid from here to and send it downwards. Then you will have a centrifugal charge pump as well for the hydraulic and pneumatic system. Then you can have a loading gear pump. So because I think you have to make this unit stagnant in a place to be able to pump something down the well. So it has to be, pressurized and held on to the ground. Then you also have your carrier engine, which is the mount itself, and the traction component, the chassis, suspensions, the leaf springs, and so forth. So you see how complex it is. How do you do a remaining life assessment on this unit? How do you judge if you want to salvage some portion of it, or if you want to just buy a new one? How do you do it? So it's a very complex scenario. So let's look at the method. So I'll just define FMCA and then we'll go straight into the worksheet because that's the most important uh, uh, aspects of this webinar. So let's look at it. So FMCA is a risk-based prioritization technique, or also a method that one can use to identify, analyze, and report the following for an equipment or a group of equipment or a process. Keep in mind, FMCA can be applied on a system level, on an equipment level, on a subcomponent level, and we'll see, we'll cover the definitions for all those types of scenarios. So you have the anticipated failure modes of an equipment. I also put in the bracket system because I think in mission critical facilities such as aviation or defense, some people use it system and subsystems rather than equipment and components. So one can also use FMCA there as well. And in also automotive industry, engineers do use the word system and subsystems rather than equipment, because the way it could fail and all those things scenarios are different. And then we can do a likelihood of all the anticipated failure modes, again for an equipment or a subsystem, and that classification is an occurrence. Similarly, consequence of that failure mode for that system or a subcomponent, and then we categorize that as a severity, also popularly known as consequence of failure, in other industry context. We'll also have the detection or the mitigation capabilities, category detection D. So you will notice I have the acronym O, S, and D, and then we're going to combine all this and have a criticality analysis of an equipment and for the components, also known as subsystems. And it's going to call the risk priority number, which is going to be a multiplication of S, O, and D. Um, uh, where it is used to prioritize and optimize resources uh, through all asset lifecycle steps: design, construction, operation, and retirement. So the primary context of this webinar is retirement because we are going to find out the remaining life of it. But keep in mind, FMCA can be used through all stages of an equipment, process, or a system. So I'll also cover the different scales, how I have defined generically the scale should look like, but one can also adopt that and modify that to suit their plant or their industry, and then use those scales as well, the severity, occurrence, and the detection scale. So we'll cover that as well. Let's look at the types of it. Bottoms up, it focuses on the individual components, and then we analyze each part separately, and then we uh, roll it up for the overall design, also known as the hardware approach, because you already have the unit built. So bottom up approach is actually heavily being used on the operational side of the things. When you're designing, you could use a top down approach. So then you can see the overall system functions, analyze this, how it could fail, and then you can inbuilt those functionality on a subsystem level, those mitigation actions proactively. Because keep in mind, a machine still needs to operate, or an asset still needs to operate with some sort of residual risk. Risk can never be zero. So this approach is also called as a functional approach, and it's also heavily being used in the industry. Criticality analysis can also be of two types, modal and item. So modal would be, you will find the criticality of each failure mode by considering the factors such as failure rate, severity, and probability of occurrence. So we focus only on the failure mode. This is applicable for the industry or for the assets in which one failure mode, so say for example, you have five failure modes applicable to an asset. But if one failure mode is so severe that it could drive the whole criticality of the unit, so in those cases, this is helpful. Item criticality is harmful where you're going to be aggregating or adding the criticality of your subcomponents, and then you arrive at an overall criticality score. So it depends on the case, the context, and the scope of your assessment. Let's look at it. And I'm also going to mention some standards which is already there. Some are, I think, the military standard 1629. This was the original FMCA standard. This is now has been, as they call it, retired, but people still use it. It's a very good one. And then you have the IEC 60812 applicable for the electrical components, and SAE ARP 5580, which is heavily being used by Society of Automatic Engineers. So in terms of oil and gas industry and process plant industry, FMCA standalone is not really a standard anywhere, but some of the API RPs like 691 and 580 do mention that example as a risk assessment, because those are risk-based machinery management and risk-based inspection study recommended practices. So those are covered there. Okay, so let's look at how the scales look like. This is just a high level example. Again, the context of the industry, your specific plant, the data you have, it's gonna all vary, and your business drivers and goals is gonna vary the scale definition. But this is how severity scale looks like on a scale to 5. So 5 being the highest, very high, and then you have the lowest being 1. You can see, I'll take one example, say very high severity level. So it could be a fatality, major injuries, replacement of main components. So you have a financial component here, you have an HSE component here, health, safety, and environmental as well. And then you have some numbers for the financial as well. Keep in mind, in cases where you do have major HSE risk, people, even though your severity could be less than this, they would still categorize that as a very high. So it's not additive, it's an or, the condition is or. It could be either major injuries or replacement of main components, either or. Similarly, if so this is one example. All the way down you have a very low, where you could have no potential injuries or safety hazards, routine maintenance is sufficient, and then non-operation for a day or less. So you have it like all the way down. Then let's look at an occurrence scale. So for occurrence, I do want to make one point here. Occurrence is like a failure rate, and it varies from the type of the asset and the industry context. And people tend to use scales interchangeably, which is not entirely incorrect, but it could be like statistically insignificant. So you must know the part you're talking about, the type of equipment, and whether there is a failure library and approved failure frequency library is available in the market, and then build on top of that, make it unique for your asset, for your facility. So this is an example. You can have a very high occurrence, which could be failure is almost inevitable, or you can have a failure more than once per day or once every 3-4 days. It really so the time frame really depends on the strategy timeline. Say for example, if you're going to build a FMCA plan for next 10 years, so this will vary. Then you will have, if it fails one in every 5 years, it's going to be a 1, a 5, like the very high, or so forth, and you will go down in terms of failure probabilities. So that's again, I will not read out each of the definition and explain this, but this is just some food for thought. Then we have the detection scale. You have very low here, you have detection being 5, and then you have very high, meaning 1. Now, why the scale is reversed? Because when you multiply SOD, so if you have a very high detection possibility, you will not let the risk priority number go up, right? So that kind of logic is built into it. Again, this will be, if it's a very high, you will have current controls, you will have effective alarms and operator rounds, and then you pretty much have fully automatic mitigation possible, and so forth. Again, it depends on the industry, your specific plant, what kind of a mitigation you have. You have to really sit in a room with operations and process and other stakeholders and define this scale as well. So this is part of the scale definition of FMCA. Let's do a worksheet. And in the end, of course, we just multiply it, and then we have a risk priority number, and then you can categorize it. So I have done 3 here as a sample, but it could be 4, 5, depending on the type of the equipment, or what you want to do. So risk priority number, if it's more greater than or equal to 75, or a severity ranking is greater than 3. So you see, I have 2 qualifiers here, because I want to make sure even if the RPN falls in this number, if my severity could be high, I want to classify that as a highly criticality ranking number 3 for my asset management. Again, it depends on the what department wants to achieve, business unit, all other factors, technical and business will play into it. Okay, what are the benefits of FMCA? I think cost-effective prioritization, because you will know where your high risk are, because it's a risk priority number, and then you will also eliminate the discretionary inspection, testing, preventive maintenance tasks, because you know which one are low risk. uh, I think I covered that. Discretionary would be, and it could also really form the basis for your inspection, maintenance, and condition monitoring budget. So, say if you are a reliability engineer or a plant engineer, you want to ask some inspection budget more, so you can demonstrate this is the risk mitigation we are achieving depending on the criticality and analysis, RPN, severance, occurrence, and detection uh, consideration. Okay. And the other, most important aspect is regulatory compliance. Sometimes, some uh, uh, regulatory authorities do let you take the credit of a risk assessment, such as FMCA, and then you can extend the, inspection intervals beyond traditional jurisdictional requirements. So for example, one would be California giving you an internal inspection on a pressure vessel extension for 5 years beyond 10 years. Every 10 years, you have to do an internal inspection based on the risk assessment and finding out that no major damage mechanisms are applicable and the risk is very low. That's one example. So it can also help in that. Okay, so let's take a look at the fun part, the worksheet. We'll do the worksheet for Airfin Cooler first. Let's see. Okay, so this is a sample worksheet. You will see the AFC component, the air fin cooler component. I have done in the bracket. I've added more description here and here, like what is the process, step, or functions under investigation. So it's going to be cooling, cooling or condensing the process fluid to sustain the production rate for a process unit or a system. Now this will vary depending on if it's a if it's a refinery or a specialty chemical plants or an offshore platform. And anticipated failure mode, in what ways the process, the function could go wrong or fail. So I have 2 here: loss of primary containment from the fin tube or the header box, and loss of thermal efficiency. And what is the impact of that? So I have the impact. So you have the failure mode, you have the impact. It could be a production loss. Again, I have not quantified here, it's just a sample. Could be a production slow down, quality loss because thermal efficiency is less. And then we could also end up doing a strategy upgrade or a major component replacement. And I have the severity scale, which is tied to here, and then potential causes of occurrence. Why this failure mode is occurring in the first place? So let's look at it. So ammonium bisulfite corrosion or a stress corrosion cracking. Again, this could be based on the material of construction, the operating parameters, which will be inbuilt to it. This is just a worksheet to explain how SOD will come into play. And then for the loss of thermal efficiency, the causes could be local hotspots. It could also be contamination, fan assembly malfunction or failure. So you'll see it's a blend of everything. You have a bundle fouling here as well. You have a bit of fan assembly malfunction as well, which is more like a dynamic component. So and then you have the occurrence scale, which is uh, chosen a category appropriate for that for the causes. And then let's see. So this is going to be happening. Anticipated failure mode. We have the severity and occurrence. Can we detect anything or can we mitigate it? So say for example, this one, the first one, leak detectors control signals because it's a loss of containment. So it has been assigned a category 3. So I'm assuming there is a semi-automatic shut off, not fully automatic. That's why it's a 3. And then you have the vibration monitoring or infrared for early detection of hotspot bundle fouling. So you have a 2 here, and then you get a risk priority number 60 and 50, which is going to land you for in a medium criticality ranking. Now keep in mind this is for one airfin cooler. So if you have say 32 bundles of airfin coolers, depending on the service and variation, you can do a similar strategy for few of those. But keep in mind if the damage mechanisms or the functional failures are different, very different, it is better to have a different FMCA worksheet for each one of them, and then you can take a look at it on a process unit level if they are connected, see and where it lands you on a criticality scale from an overall refinery standpoint. Sorry. So that's one worksheet. Let's look at the other worksheet for the well stimulation service unit. Okay, so this is same thing. I have simplified here which process step or feature is under investigation. One example, let's see, centrifugal charge pump. What does it do? It used to feed the pumping fluid to the triplex pump from the mixing tanks. This is for the acid pumping unit, WSS unit. How can it go wrong? It could be the case that no liquid is delivered, not enough liquid, and then you have pump leaking, pump works for a while and then quits. All scenarios, potential failure effects, related severities, and then potential causes. So you will see I have 5 causes here, and then each of the occurrences are assigned a ranking. And then you also have current controls and mitigation in place. It could be a direct observation if you have somebody standing there, so that there is one. Could also be a pressure gauge readings. So you will see each of the drive failure, each of the potential causes. I have a control or mitigation, and then depending on the RPN, it could be high, low. However, the scales were defined, and then I have the component level criticality as well. So which is going to be second. So keep in mind this is for only centrifugal pump. If you remember, acid pumping unit had also tanks and other as well. So depending on that, we have to aggregate it, and then we'll have a entire WSS unit level criticality ranking, which could also be a priority sequence for maintenance or could drive the replacement of the whole unit. Okay, so that's 2 worksheets. That's example. We are close to the end of the presentation, so let's take a look at it. This is the holistic FMCA method. I think it's available on the Inspectioneering Journal blog. I'm the author of that blog, so you will see the references on the last slide as well. So say I have the well stimulation service unit, you can do an FMCA. And so this holistic FMCA method is only applicable for WSS because I have conditioned that this method to specifically assess the WSS units. But I'll on the next slide we'll cover how it can be used for airfin cooler with modification, because it's a framework, right? The context, the method, the scales could be different depending on the type of the asset. So you have the maintenance history. You can do a mechanical integrity assessment on tanks and NDT evaluation. Then you have the critical rotary and packaged item. You could also do a field performance and functional test. So remember we did FMCA as well on here, and then depending on the prioritization, we might do a field performance test or not. We can decide that. So APUs, typical field tested assets components are also mentioned, and CTU coil tubing units are also mentioned here. Just as an example, to be able to relate to that. There is also an aspect of local safety regulations, so pollution control requirements for the trucks, because it's a truck mounted WSS. It's a mobile unit, right? And then the cost benefit analysis of WSS unit and its subcomponent. Like, is it cheaper to operate and maintain it, or is it cheaper to replace it? Keep in mind, if the unit goes down, your production goes down because your well stimulation service goes down. And then again, the most important component, the cross-functional team workshop to validate your entire RLA findings, and then you can come at an estimated remaining life. Okay, we can salvage some of the subunits of a truck mounted WSS, or we can just get rid of it, or even if we use it, it's going to be more expensive and so forth. Let's take a look at it for the other one, the holistic FMCA plus RCM method for air fin coolers. So you will see I have three big pillars here, because after doing an FMCA, you will have three major components. So you have the mechanical integrity part, which is more like a loss of containment. You also have the structural integrity, which will also roll up into the overall FMCA. The probability of the AFC unit failing because of structural would be very low. It's very rare that happens unless there was something wrong in the original design, but I mentioned that anyway. And the RCM. So you can have a predictive maintenance or a preventive maintenance program for the rotating components. It could be, greasing of bearings, blade and pitch angle check for the, fendering assembly, and so forth. So the key difference between the previous WSS method and this one is performance control and cost benefit analysis, because remember, there is a thermal efficiency part of it, and depending on, it's an air fin cooler, so depending on the flow rate of the air, your performance could go down or up. So one also needs to take into account those aspects as well. And then you will have the estimated remaining life of air fin cooler depending on the governing component. Could be high risk component or a major component that could bring the whole unit down, or it could be very expensive and the lead time would be very long. So that's the holistic FMCA method. I call it FMCA plus RCM because there is an RCM component to it as well. So this is for air fin coolers. We are at the end of the presentation, so these are the references, and thank you all for your attention.
All right, thanks. Any questions? I know we've got a bit of time, but not if you have any thoughts or follow up on it, would be great. And if you could put up that website again for your blog, or if you're,
Yes.
that would be great, because that went by pretty quick.
Yeah, just hang on a second. Okay, so there are actually two papers. One is this one. You guys can see it, right? The reference number 1.
Mm-hmm.
And that this was originally published. So this presentation is based on two of my papers. One was presented as a poster in a conference, and the other one is on the inspectioneering. Hang on a second. I had this chat pop up. Sorry, inspectioneering journal, and one can just look up remaining life assessment of upstream well stimulation services, and they'll find that blog. So
Okay.
I have two other papers as well on the same website, which could be helpful as well, but those are a different topic. Yeah.
Okay, cool. One thing I noticed is that I'm not a big fan of using database, or compilations of component failure rates, like for pumps or motors or stuff like that. And I know there's stuff like that for electronics. There's books and tables for mechanical devices and it's all kinds of stuff. I've always found those to be pretty inaccurate. And I mean, you would think that in the industry, and you've been using these sets of systems for years and years and years, right? You'd have your own internal data that would be a whole lot more accurate.
Yeah. Yes. I totally agree, and this is one of the caveat that I put for the especially the occurrence part of it. That scale, the probability of failure.
Hmm.
If you're using a failure database or failure frequencies from a database, it's tricky because the data might not apply to you. So a very layman example would be we play board games, right? And we have the dice, right? So we know
Hmm.
a probability of getting one number out of six is 1/6 in a single chance, because we know the total population sample size.
Right.
But if you don't know the sample size, how do you feel comfortable applying that probability of happening to your unit? You see what I'm saying? So,
Oh, it's also use conditions. They could
yeah,
be, pumping water instead of a caustic soda, and it's
yeah,
completely different effect on the system.
yeah. Yes. That's the reason I think API 581 they also modify the method of failure for frequencies by multiplying it with a damage factor, which could be derived based on the conditions at your unit. But then again,
Yeah.
those damage factor definitions are a bit vague. Like
Yeah,
they.
it's a fudge factor. The
Yeah.
217 does that too. It says, well, if it's brand new product, we'll penalize it. If it's a stable product, we'll say it's better. And if you go from vendor to vendor, that's not true. It's
Yeah, that's true.
yeah,
Yeah. Yeah.
you know,
One example I can remember is there was a material of construction change, and the API 581 was asking me to use a corrosion rate of some mils for a stainless steel. And I'm like, I just eliminated the damage mechanism altogether. There is no corrosion rate. No, no,
right.
to make the system work, the statistical model work, you have to put a corrosion rate. I'm like, that's not true. I mean, I don't care about the statistical model as much as I care about my asset management. You see what I'm saying?
Yeah, yeah. No, I think that's the good point is that you got to still think about it. It's not, open the book and plug in a bunch of numbers and you're done. No, it's got to be relevant and useful, and you bring your experience with you into that analysis.
Yes, true,
Yeah,
true.
yeah, yeah. Good. All right. So I see Carl he usually does say hello, so he does that pretty often and
Mhm.
throws out a definition of it. But I think Carl liked it, so it says keep up the good work. That's all good. If there's a handful of others still on the line, if you've got questions, head to the chat window. Let me see. I don't see anything in the questions tab. There we go. Here's
Yeah.
Carl's chiming in there.
The use condition refers to the circumstances under which the system is operated. Yes, these conditions can significantly impact the behavior and performance of the system's individual components. Yes, that is true. That is true. So you're saying conditions, operating conditions are again like some people think I have mentioned the operating pressure and temperature and that's it. No, the startup conditions, the shutdown condition, the decommissioning, slowdown conditions, all those variations also play into picture. And speaking of, how the overall conditions would impact the individual component, I'll give an example for air fin coolers again. So you have the, header box and your fin tube, right? Say you have an integrity operating window. They call it IOW in the world of mechanical integrity. And for one damage mechanism, it's a, temperature, say ammonium bisulfide. If you have water washing, then it doesn't apply regardless of the temperature. But if your header box is insulated, then the temperature comes into play. So now how do you manage that? You see, how do you manage the applicability of one DM and not applicability of the other DM to its components? So that's one example I can think when operating conditions and the applicability of certain conditions for certain damage mechanisms would influence the behavior of the individual components. Yeah, that's a very good point. Yeah.
Yeah. No, and I mean, the some standards say, well, if you're ground benign or if you're, aircraft, external to the aircraft type things, it's
Mhm.
too broad. It's too general. You still need to think through what are the environmental. You got to do that anyway for the design or for maintenance considerations. Is what is the day in the life of this system or product or component, and including uh, poor maintenance. You're on a site and they just run it and run it and run it, and they don't clean filters. They don't do the typical maintenance activities. And then that system state is completely deteriorated compared to one that's well maintained. And that's often overlooked
Yeah.
in different programs and systems. So one of my, Chris Jackson often says in his webinars is, no, you cannot check your brain at the door. You need to bring it into these kinds of analysis. You
Yeah.
need to think it through.
Yes, I agree. I agree. And with now that you mentioned about the cleaning part, I think bundle fouling in heat exchangers, not necessarily, loss of containment, loss of primary containment, but bundle fouling
Hmm.
is a big issue, and that eats up, dollars a lot. Like you don't have a leak, so you're not as concerned, but you have a slowdown, and you can't seem to figure out what to do. It's so crazy. Hmm.
Yeah, yeah, yeah. Carl's got another comment here. I haven't really heard of operational technology monitoring, but I get the idea.
Yeah, auto becoming key part of maintenance. Yes. So operational technology, I think it's different for different industries. I'll give an example for the specifically for oil and gas industry. So they sometimes they have these ER probes, electrical resistant probes, and that could send a signal, a live corrosion rate to a system in a digital control uh, panel. So those kind of things are also there. So you have a real time. So in that case, you can do the damage mechanism assessment, which one are applicable, but pretty much you have the real time data, how much it is corroding and stuff. So it is very valuable to maintain operational excellence and sustainability of the production. Yep.
Yeah, no, I've seen it more and more as sensors technology's gotten smaller and cheaper and easier to run. Um, Yet what I find is that so many companies say, "Oh, it's got all these sensors on it," and then the company that buys it doesn't have anybody that uses it, doesn't analyze it, doesn't check the data. You're collecting tons of information, but rarely, in my experience in working with different teams and stuff, they say, "Oh, we put all these vibration sensors on our equipment. Great. What do you do with it? Oh, we don't know how to analyze it.
Yeah.
Why'd you spend all that money on them if you're not going to use it?"
Um, Correct. I think I agree. So it goes back to the asset lifecycle management. Some people think
Hmm.
that they can buy and like a tech off the shelf and they're done. But that's not how
Yeah.
it works. You have to integrate that with your system. I'll give you another example. One of my so in one of my previous roles, our client used to use the ER probes and the corrosion coupons. With corrosion coupons, you take the coupon out from the corrosion fitting, and then you send it out for testing in the lab, seeing how
Right. Right.
built up. So the thing is, how do you take credit of whether it is less corrosion or more corrosion, and how does that influence your inspection spending? So if you have less corrosion, you have more real-time data. You can be more confident on your inspection data, and those specific circuits could be inspected less in terms of
Hmm.
frequencies. So those things were missing. There is one department that is doing that. That information never flows into the inspection department. They're just doing preventive inspections, schedule inspections, same scope. So I'm like, you should take credit of that, right? Yeah.
Yeah. Yeah. There's lots of opportunities, and what I'm finding is that if if you already have a great system to monitor your equipment and do all that good stuff, then the automation parts and the improved sensibility, sensoring
Mhm.
just augments that. It's good. But if you've got a reactionary type program where you only fix stuff when they break,
Yeah.
all of this analysis doesn't do anything because it doesn't change the performance of the equipment because the teams that are in charge of that ignore it.
Yep.
It doesn't matter how great your sensoring is or monitoring or modeling is if at the end of the day nobody cares or doesn't use it, and it
Yeah.
could be for all kinds of reasons. Carl asked one that
Yeah.
can AI help this effort?
Yes, artificial intelligence can and does help with this effort. I am actually, as part of my PhD on the side, researching on AI and machine learning for asset management and reliability engineering. So one of my papers is focused on how do you speed up the analysis of inspection data from non-destructive examinations, NDEs.
Hmm.
Like for example, air fin coolers, right? You have to find out the thickness, thin tubes, fouling through some means, right? Those are NDEs. How do you speed up that analysis with the help of machine learning modeling? So there are two different domains of it. One is supervised and one is unsupervised machine learning. So with unsupervised machine learning, it's just finding the principal components, like which is affecting which parameter and which are the dominant ones for our case study. For the
Hmm.
supervised machine learning, it's the name suggests it's supervised, so you know the outcome. So it's like a yes and no question. So you can use supervised machine learning to find out the defect type based on the inspection data. It could be as sophisticated as image processing from a visual inspection, or it could be as simple as feeding in the inspection data of ultrasonic thickness readings in millimeter in a tabular format, and then finding out whether you're closer to your retirement thickness or not. So I'm actively doing that as well as part of my
Yeah,
PhD.
no, that's an interesting take on it because it reminds me of one of the early machine learning AI type stuff is that
Mhm.
X-rays of somebody's lungs, for example,
Mhm.
that the AI systems were as good or better than physicians interpreting an X-ray. And there's so I and as I know that looking at vibration data, humans can pick out signals or patterns, yet so can machines, and they can do it more consistently. So it's when you got if the censoring and the data you're doing is not it's not easy to interpret and there's many factors at play and maybe it's a fuzzy image or a noisy reading that you're looking at. I see a role there for a well-trained system to become trusted that they get it right more often than not.
Yes,
Um,
totally
but
agree.
there's other parts where, if there's a hole in the side of your pipe, then and there's liquid coming out of it, I don't need AI to tell me that.
Yeah, yeah. Yeah, I get it what you're saying. So it's there are two aspects to it. One is effectiveness and one is efficiency. So where it makes sense, one should use AI and machine learning for efficiency. Where it makes sense, one should use it for effectiveness. It shouldn't be a black box. Otherwise, it's of no use, right? I mean, it's
Yeah. I mean, it seemed a lot of people are touting that you could do the whole FMEA through
Mhm.
AI and never interact with it, and you just have the report out of it. And I think that's just plain dangerous because, in my opinion, much of the value of going through the FMEA process with a team is that it develops a common understanding and the buy-in and the results and understanding of why we're taking action here, here, and here, and not following up on these other ones. It,
Yeah,
yeah, you can automate it. And you'll get a report, and in that, I've never seen those reports actually be useful, other than somebody could check it off a checklist and say, "Oh yeah, we did one." They didn't do anything with it. It had no value whatsoever, but it was done. Like
yeah,
that's
makes
not
sense.
useful.
Yeah, yeah, but I totally agree. So I'll mention one point here for the benefit of everybody. So in machine learning, whether it is unsupervised or it is supervised, whether it is labeled data or unlabeled data, there is a step called feature engineering, and
Hmm.
that's where you select your features, like what, because there are boundaries to boundaries of an assessment, right? So in unsupervised, you have to define which features are important. Same in supervised machine learning, which dependent variable is important, which independent variables are important, what
Hmm. Hmm.
to predict. And that's where the domain specific subject matter expertise come into picture. And without that, there are no models. So it should be built into it, and that's the process. But sometimes people tend to, think that since it is already built, my feature engineering step is done, so I don't have to worry about it. No, you still gotta worry about it. Yeah.
Yeah, yeah. Yeah, it's we're not there yet where it can do everything for us, including going out and fixing a pump. I heard that the other day. It's kind of my philosophy on AI. Is somebody said, it's great at checking my spelling, but
Yeah.
it doesn't help me understand that it's actually something worth writing.
Yeah. Yes. It's crazy that falls into the large language model, the transformers, and there are all sorts of variation to it, and
Hmm.
retrieval augmented generation where you feed the data, you want to limit the context, so you can do that as well. That's the reason if you enter something in DeepSeek, it won't give you an honest answer. So,
Yeah.
so there
Yeah,
are.
a friend of mine was trying to figure out what
Mm,
it's just thought, well, let me try. I'm getting ready to send, graduate, and I want to get my resume together. And, what do you think of this? And they asked me if I would review it for him. And I said, yeah, sure.
yeah.
And he said, he sent one over and he goes, now this one was AI generated. And as you know, I did not go to that university and I don't have 40 years of experience. I'm a new college grad from here, and I'm 28 years old instead. And I was like, what did you tell it to do? How did you prompt it? You got such a weird answer out of it. And it was just, here's me, my name, and I'm graduating with this degree. Write me a resume. And it filled in the blanks and all kinds of stuff. He says, I wish I was that person. I get hired right away, but I'm not.
Yeah.
But anyway, I digress. Well, I think the questions have dropped off a little bit. So thanks so much for joining us today. And thanks for the presentation. Nice case study of using this in a handful of FMEAs in particular, from my point of view, in
Mhm.
order to really make some meaningful decisions and take actions on it. So that was all pretty cool. So
Thank you so much.
appreciate all that. Thanks so much.
Thanks.
And then if we get any follow-up questions and stuff, I'll let you know. And I'll take the recordings and we'll get it posted up to Ascendo in a day or two. And also it'll also go out as a part of our podcast for Ascendo reliability webinars. And so we'll see it again in those places.
Mhm. Sounds good.
All right. Thanks so much. Have a great rest of your day.